This is lecture 40. Before we discuss clock management, we need to make a detour to talk about DMA's role in modern device I/O. And before we do that, let me just again emphasize what we discussed last time, which is here we have our software layer. So this is user mode, user space, and kernel mode, kernel space. And upper half, lower half here is some device such as Ethernet, and a packet comes in. There is a current process running, so this guy is the current guy, and we are assuming that we are performing context borrowing, because soon we will see another way of doing this which does not utilize this technique of context borrowing. But under context borrowing, which is the only technique that we have assumed so far, this current process is interrupted, and in x86 through IDT we jump to the interrupt handler. Interrupt dispatcher code like clock dispatch, which may then call a separate handler. However, this is organized, and we discussed how to organize this in 2 steps earlier. So when the packet comes in, then one chore, which I will highlight here in black. So after the packet makes its way into this buffer here inside the hardware, it has to be copied into some buffer into the kernel. And this copying inside the kernel buffer can be multiple kernel buffers, but here I'm simplifying it to focus on the main mechanics. So this copy operation is performed by a process. By which process? The current process whose context we are borrowing. And where does it copy it from? It reads from this device buffer and writes to a kernel buffer. So this kernel buffer here has as the current process, call it P1. So P1 is going to be the writer or producer, as we sometimes call, of this kernel buffer, buffer. So this one writes to this buffer. And then we talked about unblocking performed by L1. And if another process, suppose, let me show in green, this is, let's call it P2. And P2 is the one for whom the message is destined for. So P2's, or this message's destination is P2, bound to some port number as we noted earlier. At some point, P2 has been unblocked by the lower half now. Suppose it made a read blocking system call, and it's ready, and the scheduler decides when this guy becomes current. And because it blocked, it was executing the upper half read when it got context switched out. P2 becomes current, it is context switched in, it resumes where it left off. And the message that here arrived, let me go back to here, this must be copied from kernel buffer to some user buffer. We talked about that, and that's why we provide a pointer to the read system call in Unix, Linux, a pointer to a buffer, to a user buffer, this buffer here. So this is another copy operation in the minimalist setup. But who executes this? Process P2, the one for whom this message is destined for. So in this context, for the same kernel buffer, P2 is the reader of the buffer. Reader, or we also said consumer of the buffer. So this buffer here, this kernel buffer, is shared. By whom? By 2 processes. The reader the process for whom the uh, message is destined for. That's the reader. And the writer. Who is the writer? It was whoever the current process was when the interrupt occurred that signaled that a new message arrived. But there was some current process in our architecture, and that process was the writer of this shared buffer, this kernel buffer. So this kernel buffer is shared, it has a writer and a reader. And now you can uh, link this to what we discussed earlier under process synchronization, under IPC, where we talked about using counting semaphores to manage these producer consumer buffers or queues. And we said using counting semaphores is a very common way of managing a shared buffer. Shared by whom? By a writer, in our case P1, and by a reader, in our case P2. So this is where counting semaphores and what we discussed earlier in various ways are applied to make this work. So this is a very common data structure, a very common construct that's used to communicate content between a sender and the receiver, a writer and the reader of a shared data structure. And using counting semaphores that we discussed, we can assure that the shared data structure is not corrupted when P1 and P2 concurrently they access this buffer concurrently, and as long as we ensure that there's a gap between the pointers needed to maintain this circular buffer, everything is good. We don't need to use mutual exclusion to lock the entire buffer. We can use a weaker mechanism using counting semaphores so that they don't need to block when P2 is reading from it. As long as P2 is reading from here and P1 is writing to here, there is no conflict. This data structure will not get damaged. It will not get corrupted. That's what counting semaphores allows us to achieve. So this is an application where all of the stuff that we discussed under process synchronization comes into play, and we just reuse it in different specific forms to make this possible. So this buffer here, this kernel buffer, the shared buffer, it has as the writer the process who was current, whose context we borrowed to copy the content from the hardware device buffer to this memory, shared with whom? With the upper half kernel. But the upper half is just code, it's just function, it's just a library. Who executes this code? Process P2, for whom this message is destined. So when P2 resumes running, it continues from its upper half when it got blocked, and it's able then to copy this content from here to here. It's the reader of the shared buffer. So please keep in mind the mechanisms that underlie all of this operation and its intimate relationship with process synchronization and IPC that we have already discussed, and why we don't need to reinvent the wheel when we discuss device I/O and how do we coordinate lower half, upper half, and we are talking about device I/O, which seems to be quite different from IPC, where two or more processes talk to each other. Not so. Underneath it, it uses the same mechanism, because even in device I/O, a process that's running is the one that acts as the writer of this buffer, and a process that runs acts as the reader of the shared buffer, aka it's inter-process communication at the heart of it. So very, very important to make this sink in, as it's a critical element of understanding how a kernel as a software system behaves when it is architected in this particular manner. So now let's talk about DMA, which is direct memory access. And you will have covered this in computer architecture. Here we are going to illustrate its impact on kernel design for a very important killer application, which is video streaming. Prior to video streaming, we would discuss another killer application, which is disk I/O. And we haven't discussed file I/O yet. That's why I'm focusing on this. And this is the old way of thinking about how to use DMA. This is the much more challenging way. So if you understand this, then it's much easier to understand other uses of DMA. So in our video streaming, the motivation is, so here's the motivation, that you have a computing system. It could be your smartphone, it could be your laptop, your PC, and here I'm just drawing, just to make it simple, a PC. And the PC has some interface, suppose USB interface of different types, but it doesn't have to be USB. It's just needed that there's a communication interface, and there are different types of USBs with different speeds. All those details don't matter for our discussion, where we are trying to understand what's the impact on software, that is on kernel design. That's our primary focus. So through this USB, a video camera is connected. So this is my drawing of a video camera. It's sort of an old style drawing of a video camera. It's a digital video camera. And of course, they are now much smaller on the newer smartphones. There are multiple of these devices with different purposes, assisted by other sensors, etc. So here, these are the very basics to make sure that we understand how kernel comes into play. So a digital video camera, sometimes you can just use webcam as sort of a common device that we utilize, but it just doesn't have to be just a simple webcam. But whatever the quality of this device is, a digital video camera is conceptually, at a certain abstraction, just a device that takes still pictures at a particular pace. What I'm drawing here is, so here is time, and every so often, that is periodically at fixed time intervals, this camera takes a snapshot. It's a fixed picture of its environment, of the light coming in, that's then been digitized, and then it's been pixelated, and that's what it does. And that's given by, as you will have heard, by FPS, which stands for frames per second. So what that means is that if you have, for example, 25 frames per second, it means per second, so per 1 second. So this is now, suppose it's time 0, this is 1 second later, this is 2 seconds later, etc., etc. But during this 1 second interval, 25 still images are formed, 25 of them. So there are 25 of them that's taken at equal intervals. So what's the interval? You are dividing 1 by 25. And what's 1 divided by 25? That would be 40. And since this is second, this is 40 millisecond. So if the frame rate were configured to be 25, then it means This camera takes 25 still images, digital still images every 1 second, which means it takes one still image every 40 milliseconds. That's what this means. Depending upon the size of the frame, etc., this is a lot of data. So when one still image is communicated from this device, let me just call it webcam, it's communicated to our PC. Again, the same exact thing holds for your laptop, for your smartphone. It's just the specific link technology and all the interfaces that are being used, those things vary. But otherwise, the logical setup is the same. So in this case, each of these images is typically too large to send as one message. So what happens is each of these guys, so I'll pick one of them, is fragmented. It's split into small pieces. So these are all the pieces of this frame. And each piece then makes up a message, and this message then are sent over this communication link. It's a communication link using communication protocols. That's part of CS422. So we are not discussing what the software does in terms of doing the splitting, etc. Those details we don't care. But these are individual messages, packets that are being sent, and this group of packets, they comprise one frame, one still image. When these individual packets arrive at this interface card, so this is our actual interface card. So this is the interface card. So that's the hardware, which then connects to the USB wire here through an adapter. What happens is, by default, unless we do something different inside the kernel, and that's what we're trying to discuss, for each one of these small messages that together comprise a still image, a frame, for every one of these guys, when it arrives here, it generates an interrupt. So this generates its own interrupt, this guy, etc., this guy, this guy, this guy. So now you can imagine there are many such small packets that are going to arrive here at this interface, and each one of them is going to generate an interrupt. And we know what happens with interrupt for x86. The hardware looks up this table that's configured by the software, and then it jumps to the lower half code written to handle events that pertain to this interface card, in this case USB. But how often does it have to do? At the frequency by which these small packets arrive. What is a common frequency? That is, how short is the time interval between two such consecutive small packets? So what's the time interval between them? One very common default time interval is 125 microseconds. That means 0.125 milliseconds. So this is sub-millisecond. It is 1/8 of 1 millisecond. Very common number. Again, why this number? That's not part of our scope. It would be something that would be addressed in our networking course. But the point to note here is that on one such device with this particular video camera attached, by default, you would have one interrupt being issued every 125 microseconds. So per 1 millisecond, per 1,000th of a second, we have 8 interrupts just on this one device alone. We are not even talking about interrupts from Ethernet, Wi-Fi, Bluetooth. These are all separate things that may add more load if they are being used at the same time. And we are just ignoring even clocks, which ring, of course, at a particular frequency. In Xeno, we configured it so that our clock rings, we know, after 1 millisecond. But as you can see, there are many other events that generate interrupts now, which has to be handled by software, by this guy, by its lower half. This is software. And as you can imagine, with all of this onslaught of interrupts, so there's an onslaught of interrupts coming in from all of these different devices. The interrupt load, that is how many interrupts a kernel has to manage per second, can be very high. And even with today's fast processors and multiple processors, multi-cores, this would be a daunting task. That's where DMA comes into play. DMA tries to reduce the load, the stress that's imparted on the software, on the kernel, by hiding some of the interrupts. So, before we talk about how this is actually done, let me get rid of this and talk about a more advanced or a more refined design of the software layer. So this is a new picture where we start with our old picture of user mode, kernel mode, and so this is something that you're already very familiar with now. Upper half, lower half, upper half responding to system calls, lower half responding to interrupts. And for our device drivers, they have both parts as being a component, as we discussed. But now we're going to be talking about the lower half in turn being comprised of two parts. So the lower half is split into two subsystems. The one that's down here, so here's hardware. So the part of the lower half that interfaces directly with the hardware, that's called commonly top half. And the one that's close, that interfaces with the upper half of the kernel, that's called the bottom half. Obviously not the best names, but these are the names that are typically, not everyone uses these names, but these are the terminologies that is most common today. So we are just following the current practice. So just accept it for what it is, not that this is the best way to call these things. So again, the lower half now is in turn subdivided into two subsystems, a top half and a bottom half. And the top half is the guy that's close to the hardware, and the bottom half is the guy that's close to the upper half of the kernel, which of course handles our system calls. So why this subdivision of the lower half into top half and bottom half? The chief reason is that when on a device such as Ethernet or USB, whichever that device might be, and you have some event such as a message that arrives, then this message must be quickly copied from here to a kernel buffer. And typically this kernel buffer is not this buffer that I drew. There's another buffer somewhere here. And then from this kernel buffer, it typically would go to this kernel buffer, and note that this is the kernel buffer that we called the kernel buffer earlier, which was shared between upper half, this guy, and lower half, this entire guy. But now the lower half in turn, we are going to refine into a top half, this guy, and a bottom half. And now we are seeing the detailed subdivision of what may happen in typical kernels such as Linux, Unix, and Windows. So there is a responsibility to copy this message from the hardware buffer quickly to RAM memory. That's part of the kernel because this buffer is small. So the hardware buffer is very small, which means there may be other packets coming in, and certainly for USB that's true. But even for Ethernet, there may be other packets that are coming in rapidly behind it. And if this buffer is full, then these things may be lost. They may be dropped. So it's very important to keep clearing this buffer so that packets that are coming in subsequently have a place to be held and then copied over to much larger kernel buffer in main memory. So that's the idea. And who performs this copy operation? So let me highlight this in red. Yes, it's the lower half, that's what we discussed, but that's the coarse picture. This urgent operation of copying from here to here by software is the principal task of the top half. It is not its only duty, but its principal task is to quickly copy this thing from here to there. It has to do also some other things such as hacking this device so that when a new packet comes in, then a new interrupt can be issued. But those things are things that we always have to take care of. The main thing here functionally is that the top half performs this copying operation. And the top half typically will run with interrupts disabled, external interrupts disabled. So this is, of course, one of the techniques that we talked about for achieving mutual exclusion. Because this top half reads from here, that's fine, but then it writes to kernel memory, not this kernel memory, but some other kernel buffer. So there's kernel buffer number 1, which is this guy that we talked about, but then here there's another kernel buffer number 2, and then there may be even more, but here I'm just introducing one more. And this buffer tends to be smaller than this, but these are details that we don't have to go into here. But the key point for software design is that this top half code typically runs with interrupts disabled, which is perhaps the fastest way to assure mutual exclusion, to achieve mutual exclusion so that this kernel buffer is not corrupted because this guy is the writer and someone will be the reader. So this is also shared. So this kernel buffer is also shared. So for any shared data structures, we always have to be conscious and careful about not damaging, not corrupting it because of the act of sharing. Someone reads, someone writes. If they interleave, there's some kind of racing condition, then we know that data can be corrupted. That's what we discussed under process synchronization, coordination, and IPC. So we already talked about these things and the issues at hand. Same thing, we're just reusing it and applying here. So for this top half, which has to quickly, readily copy this stuff from here to this buffer to keep it safe, it can afford to run with interrupts disabled because these messages are of fixed size. So it's not like these messages can be too long. And so therefore there is a fixed time delay that can be computed, that can be estimated of performing this copy operation. So this is not linear cost in the sense that there could be 10 messages, 20 messages waiting. This is fixed. And so this can be done quickly, and because it's quickly, using interrupt disabling as a means, as a hardware supported means to achieve mutual exclusion is perfectly fine, is okay. And in this setup, we are assuming that there is some current process here that's running here, and we are still assuming that we are borrowing this guy's context to run in this example the top half, whose principal job that we are highlighting is to copy this message from here to this buffer. There comes in another message. It's empty, luckily. It's here, interrupt, copy. Then another one, empty, copy, empty, etc., etc. And this keeps repeating itself. So that's the basic setup here. So this is the responsibility of the top half, interrupts disabling and copying, copy from hardware buffer to kernel buffer. So this is what this guy's job is. What's the job of the bottom half? The job of the bottom half is when a message comes in, and suppose this is a message from a web server. So you are now using some web browser who is asking for some content from a server, from a web server, and then the message that comes in, say over Ethernet or Wi-Fi, doesn't matter. As just two examples, these messages are complicated. They're packaged like a real package with what we call headers. So these are all overhead information that are just metadata, and in some cases they have trailers. So this is stuff that's not part of the content. So the content, the pure content, we call payload. And what the application here is concerned about is the application payload. That's the file content or whatever, or the data of some HTML file that it is wanting to read. The browser is wanting to read that, or some image file. That's the application payload. But these headers are actually multi-layered, so that here within the header, this would be the payload, but the payload itself is not the ultimate payload. It in turn has its own header. It could have a trailer. It could have a trailer here. And then this guy might be encapsulated, so we call this encapsulated, by another header. So here's one header, here's another header, and then the actual content, it resides here. That's the application payload. So it's really packaged well so that it doesn't break, and this is the ultimate app payload, but it is packaged among other things. So it has to be all unpacked and processed, and much of it is done inside the bottom half. And all of this takes time. This is stuff that you don't want to do with interrupts being disabled, because it takes a lot of time, which means that when these packets are coming in and you are with interrupts disabled doing these things, then these packets may get lost. They have arrived, but they have no place to go. They are not being recognized. So you have losses occurring, damages occurring. And you want to avoid that. So the top half is the one that quickly copies over to here, and then the slower task, all the rest, and this is just one example of the things that have to be done when we're using software such as TCP. It has many other things that it has to carry out. Again, a topic of CS422. Most of these things are delegated to the bottom half, this part of the lower half. So in summary, the top half of the lower half, this guy performs duties which can be done fast. So it's like the fast half, but we don't call it the fast half, we call it the top half, but it's the fast guy. And in this case, quickly copy over, keep it safe, and let the other guys have space to hold. The bottom half is the slower guy of the lower half, but it's not slow. It's still part of the lower half, which as a whole must still be fast. But compared to the fast guy, this guy is slower. And this guy, because it can be slower, you don't want to, in general, run this guy with interrupts disabled. Instead, the bottom half which performs operations which are slower than this fast half, this top half. This guy, we don't want to use interrupts disabling, which is too drastic, it's too damaging. We want to use software technique, which is semaphores. So this subdivision of duties inside the lower half between a top half that does something that's very quick and then the bottom half, which is still fast but is doing things that can be slower than those things that can be done by the top half. That subdivision of duties is implemented, and in the design, in our reference design, top half uses mutual exclusion to guarantee that data are not corrupted using interrupt disabling. And the bottom half, which may take longer to do its job, doesn't use interrupt disabling to do its work. It uses software primitives, i.e., it uses semaphores to do its work. So here is a big subdivision of the lower half into these two different software components for these purposes. So for this buffer here, this second kernel buffer, who is the writer of this buffer? The writer of this buffer is the current process whose context we are borrowing to copy from here to here. If we keep borrowing the current process's context, so we are still keeping with our original architecture design, then who is the reader of this buffer, who then writes to this buffer? The same process. So for this buffer, under pure context borrowing, so under pure context borrowing, where the entire lower half, top half and bottom half, is performed by the same current process whose context we are borrowing, this guy copies here, this guy then reads from here and copies to this kernel buffer. And we know who the reader of this kernel buffer is, this number one buffer. We said that that's the process, some other process who is the final destination. That's the receiver process. But here is another way to architect the kernel where it's not pure context borrowing. Instead, this task of copying from here to here, that is done in this design by still using context borrowing, interrupts disabled, quick, very fast. But this chore of doing some processing on the content here, copying here, doing some other processing, all of this is performed by a dedicated kernel process. So we devise or we introduce a dedicated kernel process, a kernel thread, whose job is to carry out the job of the lower half. So two options. Let the bottom half be executed by the process whose context we are borrowing, so the entire lower half is using context borrowing, or this quick part is done by context borrowing, but the slower part, let it be done by a kernel process. That means that the kernel process is a thread, it's a process, it has to be scheduled by the scheduler, and when it runs, it's able to carry out this particular work. This looks like a nice design because it's modular, it is quite modular, and this is a separate process. But this means that when we are doing the bottom half work, we are incurring a context switch. And context switch overhead can be minimized and it can be reduced, but it's still slower in general than just doing pure context borrowing. So if all of the lower half is done by the current process, then this guy copies here, it keeps running, it copies here. Compare that overhead against this guy's context borrowed, it copies here, and then there's a context switch to this kernel thread with this guy here, this kernel process, which then performs processing and copying to this buffer. It incurs context switch overhead. So this is in general slower compared to context borrowing. But why, in some cases, do we follow this approach? It has its benefits. A key benefit is because this guy is a dedicated kernel process, you can implement the lower half code, the bottom half part of the lower half code, using blocking calls. Just keep in mind that using blocking calls inside the lower half anywhere was not allowed. It's a no-no because the null process, that is the idle process, could be the process whose context we are borrowing, and that guy should never block. So you could not, when you are coding it, when you're implementing the lower half, use blocking calls. But with the lower half now subdivided into a fast top half, a slightly or a less fast bottom half, and the bottom half now being executed by a dedicated kernel process, this kernel process is not the idle process, it's not a null process, it's a dedicated kernel process. If this guy blocks, it blocks, not a big deal. So the fact that when you have a kernel process that carries out the bottom half, that now you can implement the lower half using blocking calls, which in some cases makes coding much simpler. It's more natural, it's easier to do. That's for some cases, that is for some developers, coding for some devices, a nice feature to have, a positive feature to have. So that is its pro. So the pro is blocking calls are allowed. The negative, the con, is overhead. It will in general always have higher overhead than if we were to do pure context borrowing like what we've been doing so far. So where does this leave us? Where it leaves us is that we have an architecture now. So let me redraw this thing here. So we have an architecture now that we have refined. So user mode, kernel mode, we started from this. Then we talked about here upper half, lower half architecture. And then finally, we subdivided the lower half into the fast top half and the slower bottom half. And at the end of this discussion, we said that the slower bottom half, this guy, may be performed, may be carried out, executed, that is these instructions, by a separate kernel process. And this is only the second time where a part of the kernel, which was by default always a function, a library, a passive entity, is now carried out by an active entity. We mean a dedicated process, a kernel process. The first such instance was page out daemon. So if you go back to our virtual memory discussion, and we have to select, okay, which page do we evict to free up frames, because the memory is now all filled up, or it's close to getting filled up. We talked about a dedicated kernel process periodically waking up under certain triggering conditions, but it's a kernel process, a kernel thread. And this guy handles the chore of then running global clock and then doing the eviction business. That was a kernel process. And why would we make it into a process that performs this work? Because it was a reasonably good fit. You don't want to do that at the time when you are in trouble, because then you just aggravate your situation. So you want a process when it's not that busy to perform these tasks. In this particular case, the bottom half, which may take a while to do, is delegated to another kernel process to perform this job. It will incur more overhead, but it simplifies this design by allowing blocking calls to occur. So here is the second instance so far in our discussion of kernel design where part of the kernel becomes a process. A key functionality of the kernel becomes a process. There are a few other instances, but these are the two that we are going to highlight in this course. So there are some situations where making the chore, the task performed by a kernel to be a separate kernel process. So this is something that we don't usually encounter, is considered to be a viable option, sometimes a preferable option. Here, keep in mind the pros. The pro, I'm emphasizing only one pro and one con. Overhead versus implementation ease. That's something here to keep in mind. So this is our refined architecture. Interrupt disabling, that's done by this guy, and then this guy would utilize this instance. In general, it would utilize semaphores to achieve mutual exclusion or to protect shared data structures. And if this guy is a process, then again, this buffer here is shared between two processes. This guy, context borrowing, this guy being a separate kernel process. So it's again, process talking, process interacting with each other. IPC synchronization, all of that again comes into play. No need to have new techniques. We can just reuse the techniques that we've already covered. So this is our new updated software architecture of a modern kernel. And now we introduce DMA. So we talked about the motivation of DMA already in terms of a killer app, which really is a very stressful app in terms of the stress that it imparts on the software. So video streaming. And by video streaming, I'm including real-time video. By default, the example that I gave is a real-time video. So you're doing a real-time video chat, be it Zoom, Google Meet, whatever. We are using that even in this course when we are holding office hours and PSOs. So this is a very useful and common application today where DMA is crucial. So how does this fit into this picture? So we have again here our camera. So here's our lens. It takes pictures. It's connected by some interface, USB or otherwise, to our computer, your smartphone, laptop, PC. It doesn't matter. And it takes still images, so many per second. And each of the still images then is chunked up into small packets that then arrive at a fast pace at this interface. And by default, unless we do something different, each of these small guys generates its own interrupt. And we would have a situation where the software, the kernel's lower half, is being flooded by interrupts. On top of that, clocks, on top of that, packets coming in over the internet for your browser. Maybe you're also streaming something on Bluetooth. All of these concurrent activities which are then generating interrupts. And it's the software jobs to manage all of them. And so you can imagine that this is a tall order. So what does DMA do? It's a specific hardware support. How this is actually built into hardware has changed over time, and those details we don't care about. So here we are going to only discuss DMA from a slightly more abstracted logical perspective, which applies to older DMA hardware as well as newer DMA hardware. Those differences are not relevant for our discussion these details are not needed to understand how the kernel operates. So the basic idea behind this setup is, in our architecture, in our newer refined architecture with user mode, kernel mode, upper half, lower half, and then most importantly, top half and bottom half of the lower half. This guy being the fast guy, this guy being the slightly slower guy, and this guy optionally being carried out by dedicated kernel process, or we can just use our old technique of context borrowing for the whole thing. But whatever the case is, the situation is we have too many interrupts. So the interrupt load is too high. Even with today's CPU and CPUs, this would be too daunting a task. So we introduce another hardware device called DMA. So here is our DMA unit, logically drawn. It's not where there is this chip called DMA. That's not how it's implemented today. But logically, think of there being a unit called DMA. And these interrupts first go through DMA. So all these interrupts go through this DMA. And this DMA is a programmable device. And who programs it? Of course, software programs it. Which software? The top half, because the top half is the guy that interfaces with the hardware. That's the job of the top half. So what does the top half tell this DMA? How does it set it up? How does it program it? Basically, it does two things. It says, hey DMA, you copy these packets that are coming in, these many tiny packets, each one of which generates an interrupt. Copy them to some location in memory. So suppose here is your buffer, this is main memory. So you say, A, where in memory to copy this buffer. Okay, fine. What else? The second piece, B, that the top half informs this hardware device that will assist the software to make its job feasible is how much. And I'm simplifying this so that we can focus on the main logical architecture. So here, for example, how much means, say, 10 of them. 10 of these small packets, you, DMA, handle the interrupts. By this we mean the interrupts that are handled by this DMA do not get forwarded to the CPU or CPUs. Between the CPU and DMA, there are interrupt controllers. Again, dedicated hardware that then help out the CPUs with interrupt handling components. I'm not drawing here to just keep it streamlined and simple, but the key point is that the DMA makes it so that these interrupts, say 10 of them, how much? 10, just as an example, are hidden from the CPU. So the CPU is not being bothered by these 10 interrupts, and the DMA knows where these packets should be copied to main memory to here. So this thing arrives, the copying is done by DMA. That's why it's direct memory access, because it's directly accessing memory, in this case to copy data on behalf of the CPU to assist it so that the CPU is freed from all these numerous interrupts. So it can do whatever it needs to do to run app code. All the while in parallel, this device organizes and it manages copying, handling all of these interrupts. In this example, 10 of them. And for each one of them, these messages it directly, without intervention of the CPU, copies here to main memory. After 10 are copied, at the 11th, as an example, the 11th interrupt is allowed to go through to the CPU, who of course runs software. Top half is the software. What does the top half do? The top half again instructs the DMA, hey, copy the next 10 over to this location in memory, which would be by default the next spot, so that one interrupt, the CPU, that is this guy, it will experience, but the next 10 again are hidden. The next one it will experience, but then the next 10 it will not. Here we could make it 20. It depends on what's needed. That is, how much shielding is needed to get adequate performance. So by this DMA controller, this DMA device, assists the CPU, and through shielding the CPU from this bulk of interrupts that are coming in at a fast pace, it allows the software to do other things than just keep running the lower half interrupt code. So if this is 10, then the interrupt load is reduced. So the interrupt load is reduced by a factor of 10. So if these interrupts of these packets are arriving, as we said, every 0.125 milliseconds, a common timeline that you will find in devices, then it reduces it by tenfold, which means that these interrupts that come in make it through to the CPU every 1.25 milliseconds. Now this is much more reasonable. Our clock in Xenu on our x86 Galileo backends is programmed to ring every 1 millisecond. This is even bigger than that. So we are now in a ballpark configuration where this type of load is manageable depending upon what other interfaces we may have. This is with a factor of 10. If you increase it more, then you can again reduce, in that case we can reduce even further the interrupt load that's impinging on the CPU, hence on the software. So through this device, whose main job is now for the top half to program. So prior the top half without DMA would be copy, copy, copy. So the software does the copy. With DMA, this guy takes on the job of interfacing with the DMA and the hardware device, the DMA, in parallel to the CPU doing whatever it needs to do, but not handling interrupt code in this case. This guy is able to do the interrupt handling, it hides them from the CPU, and it performs copying. How many into a specified location in memory without having to have the CPU supervise it. The CPU only comes into play when the 11th interrupt in this example is then led through to the CPU, which means the CPU runs the top half code, and then the top half again instructs the DMA do the same thing again for the next 10 packets. So when you are doing video streaming, say for 20 minutes, you have tons of these things coming in continuously. 20 minutes is a long time in terms of computer time. And you want to make sure that all of this load is properly being handled by your software, by this guy. But this guy alone, it would be too much. But with DMA, that's architected to provide this precise support, if appropriately configured, programmed by the top half, it can alleviate this load quite significantly, so that overall the performance of this entire computing system, even with this killer app which does real-time video communication or streaming from web servers or from video content distribution systems, that the current systems that we use today, be it a smartphone, laptop, PC, even with those speeds of the CPUs that are fast but not fast enough to handle all of this load, with DMA support, it can be built so that human users who are using the system, for the most part, will think, yeah, this is actually pretty decent quality. Not perfect quality, because as you know, when you're doing video conferencing, sometimes things are not going well. And the common practice is to blame the internet. So you say, oh, the internet, it really is bad and it's causing my video to be lousy. Sometimes that's right. The internet speeds, your speed or the speed somewhere here where there's a bottleneck, that could be the cause of the poor quality that you're experiencing. But at other times, it's the software architecture and how it's implemented, the difference between how this is done in Linux versus Windows versus Unix, and other layers on top of it. When you have Android and you have iOS, all of the software layers can sometimes be the dominant factor that impacts the quality that we experience. So we call these things quality of service, sometimes quality of, so this is QoS, quality of service, or sometimes we also call it relatedly quality of presentation, QoP. So quality Q of presentation. For our purposes, they mean the same thing. But the point being, this is what the user cares about. The computing system's customer is the user, and we want the video quality to be good. What does good mean? We want to make sure that all of these interrupts are processed timely. We don't lose these small things, that they get copied and then shuffled, and then the application here, your video conferencing application, that's your process, or threads, because typically you build it with multiple threads. This is the consumer of all these teeny packets that are coming up. They all have to be processed and travel. And you don't want damage to be imparted by this layer, the software, along with the hardware. And sometimes it goes bad, it goes south. What are the specific reasons? That's quite interesting, but it's outside the scope of what we are discussing here. So just note that using DMA, this is the challenge that it's trying to address. In the software design, what does it do? This is the hardware support. Where in memory? How much? It shields the hardware, the CPU, from interrupts. This is programmed, it's configured by the top half of the lower half. And the top half's job is to supervise, manage the DMA, and if everything is properly synced and configured, then the user will get a good quality of service, a good quality of presentation experience. So that concludes our discussion of device management, except for one special device called a clock device. So we will talk about that in the next lecture.